Yes.
Okay. Hello, everyone. Thank you for coming to this week's PhD seminar. We're very lucky today to have Ilina, who's going to be talking to us about her work on Bayesian Causal Forests. So without further ado, Ilina.
Thank you. Yes, I'm going to be talking about how we use Bayesian Causal Forests for heterogeneous treatment effect estimation, and in particular, combining different data types. So, to start with first, just a bit of an introduction on causal inference. So what is causal inference? That's the process of studying the direct effect of a covariate. So for example, a treatment on some outcome of interest that we're interested in. So that's basically mean that we want to find the contrast between all the treated and the untreated subjects, which we can do. And we're basically interested in this unobserved effect of treatment if all covariates stay fixed. Why is that important? Is because one of the problems we encounter in causal inference is the confounding. So that occurs when covariates that affect the outcome also affect the treatment. So just as a quick presentation here, let's say that we have an exposure, which is smoking. So you can think that's our treatment. And we're interested in how smoking affects systolic blood pressure. So we might find some association, but this association might be partially or entirely due to alcohol consumption, which will be a confounder here, because we know that alcohol consumption is correlated with smoking, and alcohol consumption also affects systolic blood pressure. So this association that we might see might be distorted because of this confounder that we have, and we really want to kind of have alcohol consumption fixed in order to figure out the causal effect. So when we're just doing causal inference there, a few frameworks that can be used. We focus on the potential outcome framework. So we have a continuous outcome, Y, binary treatment, vector of covariates X, and the Rubin causal model, which is the potential outcome. And other ones include DAX, so graphs. And what we have the potential outcome is that for every individual that you have, you're going to have two potential outcomes. So YI1 would be the outcome if individual 1 was treated, if they kind of received the treatment, and YI0 would be the outcome given that the individual was not treated. So then the causal effect would simply be the difference between those two potential outcomes. But of course, what's the problem is that, known as a fundamental problem of causal inference, that only one of these potential outcomes is observed. So one way to fix that problem is to design studies in such a way that for a person with, say, some characteristics, specific characteristics, they get treated, and have another person with the same characteristics that's not treated. And that's the idea behind the randomized controlled trials. So subjects are basically randomly assigned to one of the two groups. If they are in the experimental group, they receive the intervention that's being tested, and comparison group, they would receive an alternative treatment or basically no treatment. They're considered the gold standard, but for the reasons we're going to see in a second, they can be quite problematic in practice. The other type of studies that can be used, these are the observational studies, but as opposed to the randomized controlled trials, the treatment assignment is not randomized there. So the researcher does not have any control over it. So imagine you go to a practitioner and they're like, look, because you're under 25 and you're female, you need to get that treatment. So basically they give you the treatment based on your characteristics, which is also the problem selection bias, and observational studies are essentially prone to the selection bias, which can occur exactly when treatment allocation is not determined at random. So just to summarize, what are the pros and cons of the two? So the randomized controlled trials, they, as we said, they have random treatment allocation, which is really good. They have high internal validity. So that is essentially how sure are we that whatever results we see for the treatment effect is basically explained by all the covariates that we have. So basically the idea that we don't have any confounding and no bias. However, they're small in sample size, they're expensive, and they have ethical limitations. Because of all kind of these small sample size ethical limitations, they're not really good for heterogeneous treatment effect estimation, because you might not always have, for example, age. You might not have very old people, or like you might not have pregnant women. So that's why they have low external validity. So that's how sure you are that when you apply your results to another population, you would still kind of see the same effects. So on the other side, the observational studies that we can use, they have high external validity because they're representative of the target population. There are no limitations there of how to enter an observational study or not. There are large amounts of data available at way lower cost than RCT. However, as we said, they kind of have a lack of a control design. And that's why they have low internal validity, because we might have some bias there due to unobserved confounding, for example. So, like Anna, as we said at the beginning, we're interested in heterogeneous treatment effects. So what is that? Is essentially the treatment effect that, in general, it varies across individuals. So, or it might be just different in the subgroups in practice. So, for example, it might be different from age under 50 and age greater than 50. That's why we seek to estimate the conditional average treatment effect, so known as CATE, as opposed to the average treatment effect. So the CATE is essentially the expectation of the difference of those two potential outcomes. Remember, YI1 was the outcome given individual I was treated, minus Y0, which is the potential outcome that individual I was not treated, conditional on the characteristics. As opposed to the 8, which is essentially, it's the expectation of the CATEs, because essentially for all units, we're going to have the same average treatment effect. So it's just the expectation of the difference of the two potential outcomes. But our goal is definitely to estimate the CATE in our case. So what are the assumptions that are made in practice? The first assumption is SUTFAN, so the stable unit treatment value assumption. So it says that there's no inference between the individuals. So for example, whether my potential outcome, if I take the treatment, won't be affected whether someone else in the room, for example, takes the treatment or doesn't take the treatment. And the second part of the SUTFA assumption is that there are no multiple versions of the treatment. So there is only one version of the treatment. The second assumption that's always made in practice when we have observational studies is the unconfoundedness assumption. So that basically means that we say, look, we say that there are no unobserved confounders. But that's, first of all, uncheckable assumption and very unlikely to hold in practice. So in the RCT, it holds because of how the design is made. But in observational studies, it's very, very hard to actually think that this is true. So that's why there is a question mark, because our goal is also to relax this assumption of unconfoundedness to be made. The third assumption that we do is the overlap assumption. So that says that there's basically no deterministic selection into treatment. So we call this the propensity score, which is essentially a probability to get treated given your characteristics. So we say that this probability to get treated is definitely between 0 and 1. It can't be 0, it can't be 1. Which again, it's the good thing about this, at least that this is checkable, because you can always see at your space whether you have probability, like whether it's essentially in your sample space where you have people with different characteristics and you have one treated, one untreated, but again, it might not hold in practice. And another thing is the overlap between the RCT and the observational studies, which we're going to talk about in a moment as well. So now that we've covered the assumption and what is our goal, let's take a look at the regression model. So we say that we have our outcome of interest and we have a function of the set of covariates and the treatment as well, and some errors. So the question now is, okay, but how do we model this function, which is essentially, it's the expectation of the outcome given the characteristics, so the set of covariates and the treatment. So what we're using in our model, but many other things can be used, is trees, so regression trees. To say what is a tree first, so what we can see, this is one example of a tree. So it's essentially a collection of binary split rows. So we see here we have two split rows. So the first one is x1 is less than 0.7. So in case, let's say that you're checking particularly for you, you know, for example, what's your X1, you check for yourself. If your X1 is less than 0.7, you're going to go to the right and then check whether your X2 is less than 0.3, depending on whether or not you're going to always get in one of these three, on that three particular, which is essentially, it partitions the input space into smaller subregions. So if you are greater than 0.7, as we can see, we're going to be that in a pinkish, orangish portion of the input space. And a simple decision tree fit is basically taken as the inputs average in the subregions that we have. However, basing your model on only one tree would be quite a scary thing to do. So that's why there are methods that use regression trees, such as the BART method, so the Bayesian additive regression trees, which estimates the conditional mean of a response variable. So just note that here, the BART method is not particularly made for causal inference. We're going to see in a moment how it's used for causal inference. But right now, the standard BART model is for just a function of X. It doesn't have the treatment yet. So it just says that we're going to present it as a sum of M3s. So that means that it's going to be the sum of all threes, where M is the number of trees in the forest, which is the preset value. And then we have function that basically maps the input of the X size to the corresponding terminal knot in the J3. Terminal knots are essentially these three. So then these M3s that we have, so just to kind of give you a rough idea of what they're in practice, they're between 50 and 200. And they're weak learners. So there will also be quite small trees. Just an example of what my forest look like. Of course, this is a forest only with 2 trees, but just to give you the idea, let's say that we have an individual that has X1 value as 50, X2 value as 221, X3 as 10. So we check the first 3 and we see that they're going to fall because their X1 is less than 50. They're going to go to the left. Their X2 is greater than 200, so it's 4, so they're going to go into that subregion that we have. And then if we check the second regression 3, so this time the X3 is less than 100, so we straight away go with only the first split rule. We don't even get to the second one. And we see that we're going to have the addition of the values in the terminal nodes here. Any questions so far? Yeah. Yes. Yeah. So, yes. So then just a bit of an idea how BART works. I'm not going to go into full details of what our priors, how do we get the posteriors, but each small tree sequentially would estimate the residual J, which is essentially the outcome minus the sum of all trees apart from the J3. And the J3, then it kind of explain a small residual portion of the variability in Y. But when all threes are added up, they basically would construct a good estimate for the mean of Yi conditional on Xi. Again, like note that here is before having the treatment. Why small trees? So they avoid explaining variability of Yi in a given sample too well, which would basically be an overfitting. And they would kind of guarantee a better generalizability to unseen data, which would be our goal if we kind of want to apply the methods to unseen data. So that's, as I said, that is like how BART is used in general. Like it's not made particularly for causal inference, but in 2011, Hill proposed that we can use BART to estimate causal effects by simply appending the treatment Z as an extra covariate. So how you can think of it now in that in all those trees that we see, one of them might be like your treatment is 0 or 1. So it might be like just an extra covariate that you can see in the trees. So it's just appending Z in the function as an extra covariate. However, yes, BART with treatment Z as an additional covariate works generally well for causal inference, but it can be problematic in some settings. And these are exactly the settings that we're interested in, that when we have heterogeneous treatment effects, the treatment effects estimates can be severely biased when there is strong confounding. And sometimes we might not even know whether we have confounding or not, because it might be unobserved. So what then can we do? So what was done to kind of overcome that issue, the authors of the BCF paper, which is the Bayesian Causal Forests model, they adapted it by doing two things. They estimated the propensity score. So remember, that was the probability that you're going to get treated given your characteristics. And then they include that estimate as an extra predictive variable. Then they also reparameterize to focus directly on the individual treatment effects. So first of all, just to also give you an idea why this is really helpful, when you're doing BART for causal inference, it was harder to get the posterior. Whereas right now with this model, you get straight away the posterior for the treatment effects. So what they did essentially, what is the new model? It says that your outcome would be equal to the propensity. So it's going to be the prognostic effect, which is, you can think of it as surface that tells us how the covariates influence the outcome. And in it, we also plug the propensity score estimation that we have. So again, the probability of I being treated, and this is the estimate of it. And then we have a second surface that is the treatment effect. So that is how the treatment impacts the outcome. And that is exactly what we're interested in, plus some errors. So that's like how we use BCF in general, but it's mainly created for observational data. In order, however, so observational data, yes, as we said, it's perfect. There's a large amount of data, but it might have problems when we have a strong confounding. So that's our goal, is to combine data sources using Bayesian Causal Forest. So the aim is to create a joint model to leverage the RCT data to kind of harness as much information from the large observational data. What are some of the challenges in general in that literature of combining different data sources? Is that treatment assignment mechanism might differ, as exactly as we know in the RCT, it's random assigned, whereas in the observation it's not. We might have confounding, which might be observed or unobserved, and the covariates in the data sets might differ, including the outcome. So it might be, for example, that you have an RCT that has a bit of a different kind of measured outcome compared to your observational study. So what do you do in that sense? And we might have some missing data as well. So just to give you an idea of what might be it, especially having the unobserved confounding, let's say that I have an outcome model that says that my outcome is equal to xi plus yi squared plus zi, so that's basically the treatment, xi squared plus yi plus some errors, where my y is unobserved confounder. So what happens is that actually my model would never know of the existence of y because it's unobserved. So that's why it's like, now that we're trying to estimate the Kate, when we can't integrate the u out, what would happen is that you can think of it that this would be a function of x, so kind of what we were doing with the BCF, but then there would be a function of u that the model would never know about. So that's where kind of the bias can come in. So because of that reason, and the same thing with the treatment. So because of that, we basically want to learn, so you can think that we learn one treatment effect or prognostic effect, as I'm going to show in a second, using all the data, but then you learn something specific on the observational data only, trying to catch this unobserved confounder. Why? Again, like because in the RCT, you're not going to have it as a confounder. Yes, you're going to be unobserved, but it's not going to causing issues because it's not going to be related to your treatment, to your treatment that you receive. For those reasons that I've mentioned, my outcome now, in which we call BCF combined model, so for combining data, we say that for the RCT, so for all individuals in the RCT, it's going to be the prognostic effect 1 of characteristics X and the estimated propensity score. Again, that's the estimated probability of unit I being treated. And then you have also tau 1 of xi, which is the treatment effect, the like given the characteristics times the treatment plus the errors. And these like mu1, which is basically a prognostic effect, is learned and it kind of appears also in the observational, for the observational study part. But on addition of that, we have a second prognostic effect, which we learn. So that's mu2 in our case, again, given the characteristics. And this time when we have the propensity score estimate, it's only on the observational data points plus, and then we also have a second surface for the tau, so tau2 xi, which is again kind of learned only on the observational study. So you can think of it as kind of trying to get that bias that can appear in the observational study. So that's okay, but when we were presenting the work, we get a lot of questions, okay, but like, how do you weight? Like, what if the observational data is severely like confounded? What happens in that scenario? Like it's completely going to swamp away your RCT. So that's why we also combine it with semi-modular posterior. But in order to represent that, first let's look at what is the multimodular settings. So multimodular settings essentially have more than 2 or more modules. So let's say that we have module 1, which have some observed data Z and parameter phi, and module 2, which have observed data Y. And I have also, I just realized that I'm very quick. Do you have any questions? I just realized that it's only 25 minutes in. Okay. Any questions so far? Yeah.
You've got different covariates in the RCT and the observation.
So that's a very good question, which we're not trying to look into that work, but it's definitely something which we're interested in the other work, because that happens a lot. And one of the main problem would be, imagine that you have a confounder in the RCT, for example, but you don't have it in the observational study. So you know that there is definitely something that would cause problems, but you haven't observed it. But yeah, that would basically kind of be a missing data problem. But we're not tackling it right now here. But the good thing is that having these separate ones, you'll be able to plug in different covariates here. So that's probably like kind of where we would start going with that one, because all of these ones, how you fit them, kind of all these 4 different surfaces, you can plug in different set of covariates there. Hope that slightly answers. Okay. Any other questions?
So Ilina, sorry. So have you think about dealing with
when is the problem to have this unobserved to you?
So also, like, let's say that if the Z, like if Z, let's say the Z might be something that is exactly equal to, I don't know, let's say 3, 5, okay, U, it might be U, it might be, imagine that your treatment, imagine that U is a binomial, Bernoulli, like 0.5, and, or like something else, it might be something 0.1. And then you might say, look, I want my treatment to be exactly as that unobserved confounder. So imagine it might be, am I female or male? And then depending on that, you know whether you're going to get the treatment or don't get the treatment. So if that's you, what we're going to have is that it's going to be xi plus ui squared plus u times xi squared plus ui. So when we kind of get it, it will be very confusing for the model what's going on. Because like you basically have, this would completely be the U on its own, but also the treatment, and it would kind of become a problem. Is that, Ioanna, what you're pointing out? Good. Everyone knows, good. Okay. So, yeah. I think it should be good because technically I have 20 minutes and I have, okay, let's ask at the end, and if we're pretty sure that we have time. So, how do I see that? Because I removed the, okay, I'm just gonna go to Zoom. Do you know what happened is that I closed it, so now I can't, here you go.
Do you want me to read it?
Yes, please.
So it's from Cheng Yang. It says, what if the outcome is non-collapsible, then you cannot read off for xi as a key.
What if the outcome is not?
Non-collapsible,
Yeah, and then after that?
then you cannot read off tau xi as a key.
Tau xi. So, okay, as Kate. Tau xi as Kate.
You come back to the
Okay, good. Yes. So, yeah, just to kind of set the modular setting, what we have, we're going to have two modules. So module 2 here essentially has observed data y, and the parameters are phi and theta. So the conventional base posterior that we know would just mean that the posterior of phi and theta given z and y will be equal to the posterior of phi given z and y times the posterior of theta given a y and phi, which is just what the conventional base posterior is. But what happens if we have model misspecification? What if one of these modules is misspecified? So the problem is that the authors of the paper kind of have the saying that if it's anywhere, it's going to be everywhere. So even if one of the modules is misspecified, there's a high chance that it's going to distort the whole model. So, and that would lead to bias and incorrect variance, which obviously not something that we want. So that's why one of the suggestions is, what do? We can do cut model posterior. So what is that is essentially, imagine that we say, look, module 2 is misspecified. So what I want here is essentially the parameter phi to learn only from module 1, but not learn from module 2. So that would basically mean that it's posterior going to be, so the posterior of the phi and theta given z and y going to be the posterior of phi given z. So if you just compare with the conventional posterior, here phi depended on, it was conditional on y, whereas right now it's not, because we kind of say, look, we're going to cut its influence on phi. And yeah, times the posterior of theta given y and phi. So you can think we're completely cutting the influence on phi. This is just another way of writing it, which you're going to see why it's helpful in a second. So another idea that can be done, okay, that's kind of completely cutting the influence. The idea behind the power posterior is that you can adjust the relative influence of the likelihood with respect to the prior. So what would that be is that the power posterior, you're kind of going to have this power eta, usually between 0 and 1, phi and theta given z and y, that's going to be proportional to the likelihood of z given phi times, and then when you want to get the likelihood of y, you're basically going to adjust this influence by putting it to power eta. So you're going to say, look, the likelihood of y given phi times theta, you can adjust it. It might be 0, 1, 1.5. But you kind of say how much you want it to influence. You kind of have access to do that. Now, in order kind of to combine the good things of the cut posterior and the power posterior, it's the semi-modular inference, which the idea of Carmona and Nichols in their 2020 paper is to basically combine this modularization and the power posterior. When they say modularization, they kind of refer to the cut posterior idea and the power posterior to allow tunable and direct flow of information. So we're basically going to say, look, rather than completely cutting the influence, I can say that I can regulate this influence here. Just to make much more sense, I'll try to explain it with this graph. Let me know if you have any questions. But the idea is the following. As a very first step, you can think that you're going to replicate, kind of mirror your data. So you're going to have y to power eta and another theta. What you're going to do here, you're going to update your beliefs about phi using a power likelihood, so kind of just what we've seen in the previous slide, where your eta is going to be between 0 and 1 on module 2. So kind of update the beliefs about phi, you're kind of going to go into that likelihood of y2 power eta, which is what we have here. And then as a second step, you're going to relearn. So you can think of it, you're doing that at the cost of your theta parameter. In order to kind of relearn it as a second step, what we're going to do, we're going to do it like kind of relearn our beliefs on theta conditional on already learned distribution of phi. So you're going to kind of think, look, theta, we're going to learn it using the fact that I know phi, which is what I've learned in stage 1. Does that make sense? And I'll try to explain it now in the easiest way possible, just to kind of give you an idea, like what happens if eta is 1 or what happens if eta is 0. So, okay, here we go. So what we can see, so remember that was my conventional posterior of the two. So I've written them all kind of in the same form, so it's very easy to see what would happen. The conventional, the cut posterior, and the semi-modular inference posterior, where again, eta is between 0 and 1. So let's take a look what happens in the scenario of eta is equal to 0. So I've given it here as an extra term, which is just 1, but just to show it. So essentially we can see all these are the same. So you can think that you integrate out the theta marginalize the theta tilt. And then if your eta is equal to 0, that would be 0. So the whole thing will become just 1, which is essentially what we have here when we marginalize it out. Then this is the same term. Then these two, basically, this what you're going to have again when you marginalize, because this is over, this is over theta tilde. It's also going to get out of it, and it's essentially going to mean that the semi-modular inference, when eta is equal to 0, that posterior would be exactly the same as the cut posterior. And that makes sense, because if you think that eta is 0, that's exactly the picture that we get when we were looking at the cut posterior. So basically, absolutely no influence. Does that make sense? Okay. What happens in the scenario when eta is equal to 1? So in that case, we see that if it's equal to 1, when we marginalize, these ones would cancel. We get exactly the conventional base. So it's essentially full influence. We're not putting it to any power. So then we combine this idea of the semi-modular inference with our BCF combined model. So what we do, we essentially say that right now, how are we going to learn the prognostic effects mu? So that's kind of how the covariates would influence the outcome. When we have the observational data, we're going to put like in the, how we're learning it, like the posterior or the MCMC, we're going to put the eta to 0 or to 1, to any power between 0 and 1, essentially. 0 if we want kind of the full cut, and 1 if we just want the normal. Because essentially, if that's 1, it's exactly the same as what we were seeing before. So the semi-modular inference is essentially, we haven't even touched it. Because if it's 1, that would be exactly the same as, as I said, the BCF combined model that we've seen before covering even the multi-model inference. So then, like, you can think of it like when it's learning that mu1, it essentially might learn only from the RCT or from both RCT and observational, depending on what my eta is. We call it a degree of influence because it basically controls the contribution of the module of interest in the inference. So just to kind of show you the idea, like how also this eta works, like whether we have a strong confounding or like not just a slight confounding, what happens? So I'm good with time, right? Okay, good. So what we do, we kind of simulate randomized data, we simulate observational data. So let's say that we have X, like just one covariate X. In the RCT, it's going to be a normal distribution, mean 0, variance 0.5. And in the observational data, it's going to be normal with 0, 1. Why is kind of that? Why 0.5, why 1? Because in reality, the RCT, the covariates that are going to have might have a smaller coverage of what actually you can see in the population. So in the randomized control trial, the treatment is randomly allocated, so it's just going to be Bernoulli 0.5. Whereas in the observational data, remember, I'm like kind of my goal is to kind of deal with these confounding issue, what in reality happens. So in order to kind of create the treatment such that it's the confounder affects it, we have a targeted selection such that we're going to have for the treatment in the observational going to be Bernoulli of phi W plus alpha I, where W is just a normal 1, 1. We have an unobserved confounder U, which is Bernoulli 0.5. And then what I put my outcome to be, which would be 1 plus 0.2x plus alpha U plus W plus 0.5x squared Z plus some errors. The errors are normal 0, 1. This alpha, as you can see, that one here and that one here, it's a constant that we predefined before that basically controls my confounding that I'm going to have. Like whether I'm going to have a huge confounding, if it's the bigger it is, the more confounding I have, kind of the stronger the confounding is. So let's say that we have a slight confounding, so I don't have much. Let's take a look what's going on. So on the left, we see the results on the observational data. On the right, we see the results for the randomized data kind of separately. One thing that you can observe, remember, like the estimated treatment effect and the X covariate values on the X-axis. What you can see, because we set it the X such that in the RCT is 0.5. That's why we see that they have a smaller range as opposed to the observational data values. So what we can see, it seems that they're all the same colors there. For the people online, at least probably you can see them, they're different. So slightly different. So what we can see here is that all of the three, so what is first of all the purple one, that's eta is 0. So you can think of full cut. Then eta is 0.5. And then eta is 1. So basically eta being 1 would mean we're not touching even the multi-modular setting, so the semi-modular posterior. And the black one is the true treatment effect. So the dashed lines, these are the confident, the intervals. What we have, you can see that they kind of all do very, very, very similarly close to each other, which makes sense because when I'm not having confounding, my module won't be that misspecified. So it wouldn't make a huge difference of which one you're using. And on the RCT, we can see again that they kind of perform very, very, very similarly. Whereas, imagine that I make A like huge, like 10. I would have a strong confounding in that sense. So then I would really need to make sure that my model doesn't lead to any bias, in general, any bias. So I would want to use the semi-modular posterior here. So what we have, what we can see is that the one that performs the best, that is kind of closest to the truth, that's the purple one. And the purple one is essentially the eta equals 0. So saying, look, I'm cutting completely. The one that does next one best is the 0.5. So that's essentially, look, you look parts of it. And then, you use only a proportion of it, and then it does better than if you use full. Then if you use fully the likelihood, kind of eta being equal to 1. We can see kind of the same trends on the randomized data in that strong confounding setting. So looks at 5 minutes, so conclusion. What we see is that combining observational data and RCT, it can improve aspects of causal inference, but we need to be very, very careful, essentially, exactly of making assumptions of unconfoundedness. When do we make them? How bias can lead into the model. Addressing unobserved confounding is crucial, especially when we're attempting to establish causal relationship and heterogeneous search. And this flexibility of eta is valuable when combining RCT and observational data. As I assume, one of the questions might be, how do we choose that eta then? Like, obviously, when you don't have simulation studies, it's you can't really test it, how close it is to the truth. So sensitivity analysis is used, and you basically held out some data and you test it just to see how it performs. And that's it. Thank you.
Wonderful. Thank you so much, Ilina. That was a really good talk. We've got a good bit of time for some questions. So are there any questions in the room or online? I'll grab my laptop. So.
I think if I can I see it?
Let's maybe start in the room. Sam?
So I'm just curious about whether the outcome is always going to be
It can be binary, because BART also have like, you can have BART with binary outcome.
Yeah, have you tried it though? Not so.
I haven't tried it with binary outcomes, no, but I know that you can do it.
Yeah. Very good. Well, at the simulation studies, what were the sample sizes of the
Oh, very good question.
how the ratio of your sample size is, for example, what if you have a switch university.
Very good question. So in that particular simulation study, the RCT is 500, the observational is 2000. If you make it like, let's say, because we've tried with Ioanna making it like the RCT only 2 and the observation, I don't know, like 1000, it's kind of crash in the sense that it's the BCF always, like, as you can see here also for the randomized, it always kind of goes towards 0. So that's the idea, because it doesn't have much information, especially from the RCT, it just goes to 0, just kind of search to 0. So that's the main problem. Can you change that?
You have to run.
Oh, sorry. Then I'll say you can. Can I see it? I can take a photo.
Save it.
Because I'm also not quite sure what you mean by non-collapsible. Because if the outcome is continuous, what is non-collapsible? Yeah, that's my question. Like, if it's
I think you might be referring to the fact that Kate is actually a different function, different surface in the observation. I don't know.
I would ask him, because yeah, no,
you might have to go in a minute, but he's talking about binary or survival.
Oh, okay. Yes, because that's why I was going. So yeah, it's kind of. So I haven't tried it, Chengyang, with binary. That was also some question, but I haven't tried it with binary outcome.
So I'll read this out whilst you.
You want to read?
Because it's not on the screen for other people.
Oh, sorry. Yes, you can read it. Go for it.
So there's a question online from Eman. She says, when you considered one of your models could be misspecified, is there also a chance that you either wouldn't more know which one is misspecified, or that more than one is misspecified? In this case, can you expand the same correction method?
So we believe that the misspecified one would kind of come from the observational, because like that's where you can kind of have this bias that can lead into. But in general, like, I'm not quite sure if you maybe if you try two observational studies combining, what you do in that sense. We haven't tried that, but that would be interesting, because what if you have two observational studies? Like, which one do you think is misspecified? I would assume that you need to do kind of some sensitivity analysis just to check what's going on, or use some prior information if you know something on it. Yeah.
So I have a question on, starting from the last things that you said on the posterior, and then the conventional one, and then the semi-modular inference one. So you said that in the simulation studies, if you have little confounding or slight confounding, then there was not much difference in the curves. And then, so my first question would be, in that case, is the posterior the best choice because it's more parsimonious, or the fact that eta equals 0 is more parsimonious is a misinterpretation of my?
I would say that if there's little confounding, I would go with eta is equal to 1, because you still get more information from the observational data. And if there's no confounding, you're basically just increasing your sample size, which is good. Because like also eta 1, when you have little one, it has like the tighter interval, if that makes sense. So that's why I would go with eta 1, which is the conventional one, yes. So that's basically like tells us that this semi-modular inference would be helpful if we have confounding, but we might not need to make our model more complex if there's less confounding or no confounding.
So if there's like less confounding or say not much confounding, you would want to take in more information, so you wouldn't cut that pathway. Because the information is not tainted or contaminated, so we want it.
Exactly.
So there's not an advantage for going for the one person.
I think that's what my personal thought is, yes.
Okay, so that would answer my question, because I thought that it said, since it was more parsimonious, then we would prefer that one, but then when there is confounding, we prefer eta equals 0. So
I would also say like if you also tried with eta 0.1, might also be very, very close, because again, you're kind of taking some information. Again, you're not completely cutting the observational.
Okay. And so then that leads me to my question of the sensitivity analysis. So you said we usually choose eta using that sensitivity analysis. How would you do that? Do you have like a measure that usually you look at to say which is the optimal eta, or do you look at plots?
I would say you need to also look at plots just to kind of see how they're doing, and kind of, let's say that you see like a few values that are very close to each other, and you'd also like imagine you held out some data, like you then test it on, and you kind of do the test of fit just to see which one that's better. And if you see a few values that are very close to each other, you would know that probably the best one is around those values.
So if you see a few values of eta for which the curves are next to each other?
Yeah, so imagine like you test like 0 and 1, and they're completely different. Well, let me think actually.
Then that would mean that there is
that would mean that there's confounding. So then you'll be like, okay, like I want to make sure that it doesn't lead into a lot of bias. So you kind of want to be on the lower side of the eta. And you're going to maybe try 0.1, 0.1.5, 0.2, kind of see which one around those would do best.
You choose the highest among the lowest ones because you want to try to get information.
Exactly.
Okay.
Yes. You?
Are there any more questions in the room? Any more questions online? Yeah.
Have you tested the average of your?
Yeah. So on average is 95, 96%. In comparison, BCF does 80, 85 on average. Again, it really depends on what the scenarios are. Yeah.
Yeah, I'm going to this one. How about exactly affects the strength of the confounding and concentration?
Can you repeat again? Strength of compounding?
Strength of the what exactly affects the strength of the confounding and
Well, eta, you are the one choosing eta.
okay.
So before you start, you need to know what your eta is. Well, we can kind of tune it. You can try different values, but it's not learn from anywhere. Of course, you can do sensitive analysis to try and learn it. But yeah, it will really depend on what your scenario is.
So what's your time?
What to get?
What you look at?
What do I get?
What you look at to see that.
I think we might be running out of time, so maybe.
Let's
discontinue
just,
after.
yeah, yes.
But if everyone can join me and thank you, Ilina, again for
Thank you for the people online as well.
and thanks for people online. We'll be back in 2 weeks' time, on a different day of the week, in a different time, in a different place, and I will be speaking. So, see you then.
How do I stop it? I don't think I can do anything on my side.